Hello and welcome to one short revision of class 10th physics. Here in this lecture we are going to study about the theory concepts of light, reflection and refraction. So light basically a form of energy. Its speed is 3 into 10 to the power 8 meter per second, that is in vacuum, or we can say in air. It's approximately same, it's 2.99 something, but we consider it to be same. It always travels in a straight line, that makes sure. Okay, so basically we are going to study two concepts. Reflection means bouncing back of light in the same medium. Light is coming like this, falls on a surface, reflect back. This phenomena is reflection. And the second concept is refraction, in which light comes in from one transparent medium, falls on a surface and moves into another transparent medium. For example, light coming from air and enters into the water. That is refraction. So we are going to study about two concepts. Beside these two concepts, there is one more definition in your NCERT of diffraction. And diffraction is basically bending of light from the corners of any object. You don't have to study about that. In reflection, you are going to study about the laws of reflection. You are going to study about the types of mirror. What is mirror? What are the types of mirror? Lateral inversion is a concept related to the reflection in mirrors. Some terms related to the spherical mirrors, ray diagram rules. Ray diagrams are an image formation by spherical mirrors, sign convention of the spherical mirrors, and mirror formula and magnification. This you are going to study in reflection concept. In refraction, you are going to study about the refraction through glass slab. You are going to study about the laws of refraction. You are going to study about the refractive index, Snell's law, terms related to the spherical lenses, ray diagram rules, formation image, sign convention, lens formula, magnification, and power of lens. That you are going to study in refraction concept. Besides these concepts, you are also going to study about the real and virtual image, which are very important and is common in both. That means in reflection concept and in refraction concept. A little bit of definition change. So let's start with the reflection. Reflection is basically bouncing back of light in the same medium when it falls on a particular shining surface or a plane surface. Okay, so let's consider this to be a plane surface, and one side it is highly polished, just like a mirror. Mirror is a glass and one side it is highly polished, so that all the light falling on it bounce back in the same medium. Maximum amount of light, 99.9% amount of light bounce back in the same medium. This happens when the mirror is highly polished. The polish is not gone. Okay, so basically we are going to study about the laws of refraction. Reflection, in this law of reflection, when incident ray, that means a single line, a single ray, when falls on a mirror, it bounces back in the same medium at that particular point on which the light is falling. This point is known as point of incidence. This is point of incidence, and at point of incidence we draw a perpendicular to the surface. This is surface and this is perpendicular. This perpendicular is known as normal to the surface. And laws of refraction contains two statements. The one is angle of incidence, that means angle between incident ray and normal. Okay, this angle is equal to angle of reflection, that means angle between normal and reflected ray, that means this angle which I am darkening. Okay, so these two angles are same at this point of incidence. So this is your first law of reflection. The second law of reflection says incident ray, reflected ray and normal at the point of incidence to the surface, they all lie in the same plane. That means out of the plane, nothing will go out of the plane. Each and everything would be in plane. So these are the two statements of laws of reflection. If we talk about the types of mirror, okay, so basically there are two types of mirror. One is plane mirror. This is a plane mirror. Okay, this is glass plane, and other side is polish, and the light travels and bounces back at the same medium. And the other one is spherical mirror. So spherical mirrors are basically a part of a sphere. Spherical mirrors are of two types, concave and convex. We are going to study about them. Now see, consider a large ball I have a large ball of glass, and I take out a portion of that glass. I have taken out that portion. Now that portion can be polished from inside, can be polished from outside. If if suppose this is a portion of glass slab, glass ball which I have taken out. If I have polished it from inside, the reflecting surface would be from here. The reflection will come from here, like this mirror. It is polished from this side. The reflection surface would be this one. So this would be convex. And when the polish is outwards, the reflecting surface would be inwards. This would be concave. To learn it, make it cave in your hand. This is concave when reflection is happening from this side, and this is convex. Concave and convex. Two type of spherical mirrors. So you can see this is a convex mirror. We are going to study about the properties. It is slightly curved outwards from the center, like this. This is surface, reflecting surface. Light will come from this side. Now there is a concept of lateral inversion. Now what is lateral inversion? You have seen when you see yourself in a mirror, you see your image to be inverted. Your left is the right of the image you are seeing inside the mirror. So what happened? Suppose this is an object. Now we are going to study about the property of its image. This is mirror. The head suppose this head is at x unit from the mirror. The image head would also be from the x unit from the mirror. And if the tail is at the y unit of from the y unit of the mirror, then the tail of the image will also be from of y units from the mirror. Now the image is inverted. That means it was like this, and now the image is like this. So the image we got is virtual, erect, in plane mirror. Erect means it's upwards, same size, but we get laterally inverted. And this lateral inversion is a phenomena in which image gets inverted. Now talking about the image, there are two types of image. One is real image, one is virtual image. Real image we obtain on a screen. That means the light, if it coming from suppose this is a mirror, if two lights are coming like this, after reflection it meets at a point in real portion. If I keep a screen here, the screen can be anything, like a wall, like a screen, like particular page or copy or anything. It's a screen. If light after reflection meet at that particular point, then that type of reflection is said to be real image. The image formed as real image. And now a real image is formed on a screen. The reflected ray meets at particular point to give a real image. The real image we obtain in a plane mirror. We basically don't obtain in a plane mirror because light after reflection does not meet. We obtain real image in spherical mirrors, and the image formed is always inverted. But the image can be diminished, can be magnified. Diminished means smaller than the size of object, can be magnified, can be of same size. Okay, so these are the properties of real image. Now talking about the virtual image. Virtual image we get inside the mirror. We look our face inside the mirror. Okay, now when we look inside the mirror, we see ourselves inside it. So the virtual image we get inside it. The reflected rays diverge from a particular point. The reflected rays will come like this, and not from the plane mirror but from a spherical mirror. The rays will come like this and will diverge. So when we look inside the mirror, it seems the light is coming from inside, from a particular point. The image we get is always erect, and the image can be diminished in spherical mirrors and same size in plane mirrors. So these are two types of image. Also, the image can be of regular reflection and diffused or irregular reflection. This is a plane mirror. Okay, the image we get is perfectly okay. The light, suppose, come and reflects at particular point. The image we get is always regular. But this is also a plane mirror, but I have taken out polish from here. If suppose I use it, I throw a light on it, see, some part of the light is bounced back behind the mirror on the wall. So if the polish is not proper, if the surface is not proper, or if the surface is like wavy, which you have seen in mirror maze in fairs, so in both the cases we don't get a perfect image of the object, and that type of reflection is diffused reflection. So there are two types of reflection, regular and diffused. Now if we talk about the spherical mirrors, we have seen there are two types of spherical mirrors. These are the two types of spherical mirrors, convex and concave. Outwards from the center reflecting surface, this is convex. Inwards, this is concave. Okay, so we have seen spherical mirrors. Now let's talk about the terms related to the spherical mirrors. The first term is pole. Pole is basically the centermost point. Suppose this is a spherical mirror. It is spherical not because of the surface, but it is spherical because of the curvature. ये curved है. Because of the curvature, this is spherical mirror. So the centermost point of this reflecting surface is pole. Center of curvature. If I complete this a complete sphere, if suppose I complete this in a sphere of which this mirror is a part, then the center of that particular sphere is known as center of curvature. Now the next is radius. So center of curvature to this pole, the distance is radius of curvature. Now there is an imaginary line which joins center of curvature and pole, that is known as principal axis. Now what is principal focus? If light rays parallel to the principal axis, they are coming. If light rays parallel to the principal axis, after reflection, they will either meet at a point, that means converge at a point, or they will diverge from a point. That point is known as principal focus. And the distance between principal focus and pole is focal length. And one more thing, there is an aperture. The openness or closeness, this diametrically distance, this openness or closeness is aperture. Let's see all these terms in particular in this diagram. This is the curved inwards, that means concave mirror. So this is a part of a particular sphere. The center of that sphere is center of curvature. Distance from center of curvature to the pole is the centermost point of the mirror. This distance is radius of curvature. Focus and pole distance is focal length, and this openness and closeness is aperture. So these are the terms related to spherical mirrors. You can pause the video here. You can learn all the terms related to the spherical mirrors. These are the definition you can learn from here. Now this is convex mirror, same, but in convex mirror, this is a convex mirror. The reflecting surface is outwards. So curvature and focus all will be inside, that means virtual. Focus and center of curvature of a convex mirror are virtual. Okay, so keep that in mind. This will be useful in our further topics. Now there are some rules to make the ray diagrams of convex and concave mirror. Basically, to draw light rays, we have 4 rules in mirror. The first one, if light is parallel to principal axis. Now I am talking about a concave mirror right now. We'll be discussing about the convex mirror in the second topic, after this topic. If light is parallel to principal axis. So C, this is F, this is C, this is P, and this is reflecting surface. If the light is parallel to principal axis, or I can draw it other color. So after reflection, the light will pass through focus. This is your first rule. So parallel to principal axis, pass through focus. Second one, passing through focus, then this is convex, sorry, we are discussing about the concave right now. This is concave. Now see, if a light ray is passing through focus, so after reflection it would be parallel to principal axis. It will be parallel to principal axis. These are the first two rules. Let's see the third rule. First, parallel to principal axis, pass through focus. Second, passing through focus, parallel to principal axis. Third, if passing through C, that means center of curvature. So any line passing through C on the mirror will be normally. So angle of I equals to angle of R, that means 0 degree. It will retrace the path. So if any light ray passes through the center of curvature, it will retrace the path. It will retrace the path. Okay. Now the fourth rule, if fall on pole, if a light ray is falling on pole, then we have to follow angle of incidence equals to angle of reflection. All these measurements should be accurate, so use ruler, use a sharp pencil for making angle. Better to use protractor. Do not mark approximate diagrams. Always practice from ruler, a sharp pencil and protractor. To make curvature, you should use compass. Okay, don't make rough end diagrams. Now let's see about convex mirror. The first rule, line parallel to principal axis. This is a convex mirror. Now see, in these cases, in the concave cases, all the light rays and the terms, that means F, C, they are on the real side. We follow basically some rules that the light will always be coming from left side. The alignment of the mirror should be like this, that light is coming from the left side and reflection is counted after that. So F, C and light all are in real, that means these points are real. But in case of convex, the light is coming here from the left side, but F and C are not in the real side, that means they are in the virtual side. So after reflection, it will appear to diverge from a particular point in case of convex mirror, and this point is principal focus. That's your first rule. Second rule, make sure to practice of convex mirror a lot, because questions from convex mirror are coming in the previous years. So there is a chance, there is a possibility that it will come this year also. So make sure to practice a lot. Now if suppose the light is falling on focus, it won't fall directly, but it will point on a particular point. After reflection, it would be parallel to principal axis. That is your second rule in convex mirror. Third was passing through C. Now passing through F and passing through C in convex mirror are very important because C and F are virtual. So they are lying from outside to inside. Okay, see this is P, this is F, this is C. If a light ray is passing through C, it will retrace the path. And the fourth rule and first rule are easy. F, C, angle of incidence equals to angle of reflection. So these are the four rules basically we use to make ray diagrams in these mirrors. Now see, these are the ray diagrams. This is a table and ray diagrams of concave mirror. When the object is at infinite, I'm talking about the object. If the object is at infinite, the image would be formed on focus. That means all the light rays will come parallel to principal axis and after reflection will meet at a particular point. That point is principal focus. So see the diagram. The light rays are meeting at a particular point. This is principal focus. Image would be real. That means would be obtained on the screen, inverted, upside down, and highly diminished. If we focus sun, we'll get a point size image. That means they are highly diminished. The sun is very large, very huge, and we are getting a point size image. That means very, very highly diminished image we are getting. If I'm bringing object from infinite to near the mirror, the image will start shifting from focus to ahead of the mirror. Now see, if the object is beyond C, that means C is here and the object is kept here. So after reflection, the image would be formed between F and C. The properties of image would be real, inverted, and diminished. If I keep object at C, we will get the same size, real, inverted, and at C itself. Now I am bringing object near and image is shifting like this. First, when the object was at infinite, the image was at F, beyond C, between F and C, at C, at C. Now the object is kept between F and C, the image would be beyond C. So now that's the fourth point. When the object is kept between F and C, the image is beyond C and the image is real, inverted, and enlarged. And this is how the diagram is made. When we keep the object at F, the image we get at F, the property is real, inverted, and highly enlarged. And the sixth case, only this case will get virtual image, and this is very important. When the object is kept between F and P, the image, see, when the object is kept between F and P, the first ray will go like this, the second ray will go like this, both the rays are diverging. So we have to extend it inside the mirror and we get a virtual image. A virtual image is magnified. Only in this case, it is magnified and erect and behind the mirror. That means inside the mirror. So these are the 6 ray diagrams we use in concave mirror. Talking about the convex mirror, because convex mirror all the positions are virtual, so we only take 2 positions when the object is at infinite and when the object is between infinite and near the mirror or pole. So these are the 2 images. Light rays coming parallel will pass through, will diverge from focus, and light ray coming from the nearby mirror, it will form diminished image. In both the cases, we will get diminished image, erect image, and virtual image. Now talking about the uses, concave mirror are used in torches, searchlights, or flashlights, or the lighthouses nearby the seas. All uses concave mirror. When you can imagine the last case. the light rays are diverging. So when we need diverging light rays, we use concave mirror, the last case. In solar furnaces, we use concave mirror when the water is kept. Suppose we are talking about the water, solar water heater, and the water tubes are kept at focus. All the heat rays coming from infinite are converged to the focus, and heat will get, and the water will get heated inside the tube. Dentist mirror, what they have a small mirror, and they put that mirror inside the mouth and to see zoomed in image. So zoomed in image, magnified image inside the mirror, sixth case, that would be dentist mirror. Shaving mirror, again we keep it like this, and to see if suppose if suppose I do shaving, and to see if hairs are left or not, we use shaving mirror. Now vehicles headlights. The headlights of the vehicles are also concave in shape, and the configuration of light is at 2 point. You must have seen low beam and parallel beam or high beam in vehicles. High beam, the bulb filament is at F, so light goes parallel, and low beam spread out configuration, that means between F and P. Talking about the convex, now since the light rays are converged in concave mirror, the concave mirror is also known as converging mirror, and lights are diverged in convex mirror, so it is also known as diverging mirror. Talking about the convex mirror, they are used in rear view mirrors, they are used in parking mirrors, they are used in traffic mirrors, T points. You must have seen a big mirror nearby the T points or nearby the U-turns, so that traffic may see whoever is coming from the other side. In malls and complexes, you must have seen a big mirror on the corner, so that the counter, the person sitting at the counter can see the whole view from that particular mirror. So whenever we need a wider view of angle and virtual and erect image, we always use convex mirror. That's why they are used in rear view mirrors. And because they use wider view, the image is diminished, and that's why there is a warning written on rear view mirrors. Objects in the mirror are closer than they appear. Because the objects seems to be diminished, we think that they are far, but they are not far, they are nearby. Now talking about the sign convention. So what do you mean in the sign convention? We have seen some terms like object distance, focal length, radius of curvature, and image distance, and so on. So all these have to be counted in terms of particular units, distances. So distances, how we count? You must have studied the Cartesian plane in mathematics. We take that same plane, we take concave mirror, and we put concave mirror in the plane such that the pole and origin coincides. Okay, all the distances are measured from origin in Cartesian plane. In mirrors, all the distances are measured from pole. Now light always comes from the left side. Light, that means object distance is denoted by u. So object distance, u is always negative, always. Now f is focal length. F of concave mirror, again f is here, c is here, so f is again to the negative x-axis, that means negative. C, center of curvature, C is also negative. C basically gives us radius of curvature, so R is negative, and radius of curvature is nothing but twice the length of focal length, or we can say that focal length is R by 2. Okay, so we have U, we have F, we have R. Talking about the image distance, V is image distance. So we have seen six cases, out of which 5 cases are giving me real image, And the sixth case is giving me virtual case, virtual image, magnified one. So in case of virtual, the image is obtained here, it is positive. In case of real, all the images are formed here, so they are negative. So concave mirror, real images negative, concave mirror, virtual image positive. Talking about two more things, height of object. Height of object is always kept upright, that means like this, in the positive y direction, so it is positive. And image, if image is real, we are getting it downwards, so negative. If image is virtual, we are getting it upwards, it is positive. So these are the sign conventions of concave mirror, and these are used in numericals. We are not going to discuss numericals in this lecture. We are just going through the theory topics in this lecture. Now see the sign convention of a convex mirror. Same, we'll draw a Cartesian plane. All the distances are measured from origin. We are keeping pole on the origin. F is here, C is here. So in this case, use object distance, always negative. F of convex mirror is positive because it is in the positive x-axis. R is positive. The images formed are always diminished or at F. So image is always positive. That means virtual image in convex mirror is positive. Height of object is always positive, and height of image, because both the images are forming upright, erect, they are also positive. So in case of convex mirror, these are the sign conventions we are going to follow. Talking about two more formula in this, on the basis of which all the numericals portion come. Magnification. Magnification gives the ratio between height of image and height of object. So m is minus v by u. V is image distance, O is object distance. You have to keep v and u along with their signs, and that is equal to height of image upon height of object. Mirror formula is 1 by f equals to 1 by v plus 1 by u. Let me give you some insight about the magnification also. If m is positive, that means height of image is also positive and object is also positive. That means we are getting virtual image. If m is negative, we are getting real image. If m is positive and equals to 1, so it is a plane mirror. If m is positive is smaller than 1, it is convex, because in convex mirror we are always get diminished image. And if it is positive and greater than 1, we are getting concave mirror. The last case, sixth one, magnified image. If m is negative and the value is between 0 and minus 1, keep that in mind. In integers, minus half is bigger value than minus 1.5. So if the image, if the magnification is negative and between 0 and minus 1, 0 say minus 1, then in this case the object is either at infinite or beyond C. If we are getting minus 1, then the object is at C. If you are getting the value bigger than minus 1, sorry, smaller than minus 1, that means minus 1.5, minus 2, minus 3, minus 4 and so on, then the object is between C and F or at F. So these are the insights of magnification we get in convex mirror. That's all about reflection topic. Now getting back on the refraction. So talking about the refraction, what is refraction? Refraction is the phenomena in which light, when comes from rare medium, suppose this is a rare medium, this is a denser medium. Now what is rare, what is denser? Suppose consider to be air and water. Water seems to be optically denser, heavy. So water is a denser medium, air is a rarer medium. So when light comes from rare medium to the denser medium, at point of interface we make normal. After refraction it will move towards the normal. So this bending of light, when the light travels from one medium to another medium, gives this concept of refraction. Concept of refraction, again, to maintain the speed, basically speed of light is 3 into 10 to the power 8 meter per second. Okay, so to maintain the speed is distance upon time, that means wavelength upon time period. So to maintain this speed, it shortens its distance. Okay, that means wavelength gets effect, and hence the light move either towards the normal or away from the normal. Light, when coming from rare medium to denser medium, moves towards the normal. From denser medium to rare medium, it will move away from the normal. Suppose this is a denser medium, this is a rare medium. If light is like this, so instead of going like this, it will move away from the normal. So that is the concept of refraction. Okay. Now talking about a glass slab. See, this is a glass slab. It is a cuboidal, transparent medium bounded between parallel surfaces. It is a cuboid, basically, a transparent cuboid. So in this case, what happened? This is air, this is glass, this is again air. When light comes from air to this, at this point of incidence, it will move towards the normal. At this point of incidence, it will move away from the normal. And if we extend this line, we will get parallel line. So now naming them, this line is incident ray. This is angle of incidence. This is normal 1. This is angle of refraction 1, R1. This is R2, angle of refraction 2. This is second normal. And this is angle of E, emergent ray. And this was original path. So because the surfaces of cuboid of this glass slab are parallel, we get the emergent ray to be parallel from its original path. The distance between these two parallel lines is known as lateral shift. So this is basically the shift between original path and the emergent ray. The glass slab, you can see, this is a glass slab. I'll drop a video after this lecture, and the light ray will, I'll show a video, will record a video and will be uploading. The light ray will bend towards the normal and away from the normal in this. Okay, I will drop a video. So these are the concepts. This is the practical which you have already performed during your internals, and these are the concepts related to the glass slab and refraction. Now there are two laws of refraction again. First, the incident ray, refracted ray, and normal to the interface at point of incidence all lie in the same plane. Nothing would be go out of the plane. All lie in the same plane. And the ratio of sine of angle I, that means this angle I, and the ratio of sine of angle R, that means sine I upon sine R, sine trigonometry, sine I upon sine R is always constant for a given pair of medium for given color of light. They're always constant. So that's your laws of refraction. Talking about the Snell's law, this second law of refraction is also known as Snell's law, which again states the same, that ratio of sine of angle of incidence to sine of angle of refraction for a given pair of medium for a given color of light is always constant. Now talking about a concept, refractive index, how much bending of light would occur. Okay, so refractive index is basically change of direction that takes place in a given pair of medium when is expressed in term of refractive index. Okay, refractive index is that particular constant which we have obtained in this Snell's law. You know that light, the speed of light is 3 into 10 to the power 8 meter per second. We consider, suppose there are two medium, light is coming from medium 1 to medium 2. So we express like this, n2 1, that means refractive index of medium 1, medium 2 with respect to medium 1 is v1 upon v2. That means speed of light in medium 1 upon speed of light in medium 2. And if medium, basically this ratio is known as relative refractive index. So relative refractive index is refractive index when two different mediums are counted. It is ratio of speed of light in medium 1 to the speed of light in medium 2. And absolute refractive index when one medium, when the first medium is replaced by vacuum or air, then we say the refractive index of that particular medium is speed of light in air to the speed of light in medium. That means C upon V. C we represent by speed of light in air, that is 3 into 10 to the power 8 meter per second. So all the speed will be smaller than 3 into 10 to the power 8 meter per second, and hence C by V, the ratio of C by V would always be greater than 1. So absolute refractive index is always greater than 1. For example, the absolute refractive index of water is 1.33, of a normal glass is somewhere around 1.5, of a diamond is 2.42, and so on. It tells how much, to what extent the light will bend when it travels from one medium to another medium. Now again we have different types of lenses. This surface was convex. And this is also convex. If I join two convex surface, we will get convex lens. Because both the surfaces are convex, we also call it double convex lens. Same goes for double concave lens. Both the surfaces are concave. We also have some types of lenses like plano-convex, plano-concave, concavo-convex, and convexo-concave. But you don't have to study about them, so don't worry. Talking about some terms related to the spherical lenses. Again, there are some terms. You can pause the video here so that you can take the screenshot. You can learn all the definition. Center of curvature, when both the surfaces are part of a particular sphere, the center of those sphere is known as center of curvature. For now, for all the study related terms and all the concepts, we take the center of curvature of both the surfaces to be same. That means the radius of both the surfaces are same. Principal axis, an imaginary line joining center of curvature and the centermost point of the lens, that is known as optical center. So optical center is the centermost point of the lens. Aperture, the effective diameter between the end points is aperture. Principal focus, all the light rays coming parallel, if after refraction meet at a point or diverge from a point, That point is known as principal focus, and the distance between that particular point to optical center is focal length. So this is a convex lens, this is focal length, this is radius of curvature, this is aperture, this is optical center, and see, this surface had, suppose this is first surface, this surface, this convex surface will have all the terms here. So f is here and 2f is here. This surface 2 will have f2 here and 2f2 here. So all the points in this case are real. We are getting in real world. So keep that in mind. Convex mirror was virtual, but convex lens is real. Same goes with concave lens. This is the first surface, same side, f1 and 2f1. So light refract and goes in the second side, but this would be imaginary side, virtual side. We will see the ray diagrams of this also. So this is concave lens. Now, talking about the ray diagrams, the rules of concave lens and convex lens. Since we have seen 4 ray diagrams in convex mirror and concave mirror, we are going to use 3 ray diagram rules in convex lens and concave lens. So talking about the convex lens, if light is parallel to principal axis, then after refraction will pass through focus. See, this is convex lens, f1 to f1, or f or a 2f, f to f, f to f. The distances should be same, should be calculated and drawn with the help of ruler, sharp pencil and compass. The light parallel to principal axis, after refraction will go through focus. So that's your first law, first rule to make the image diagrams, to make the image formations. The second rule, if the light is passing through focus, second, passing through focus. So after refraction would go parallel, parallel, focus, focus, parallel. This is your second law. And talking about the third law, if the light is passing through O, that means optical center, it will go undeviated, that means as it is. So the third law, from O, it will go as it is. Talking about the concave, F to F, F to F. Light coming from parallel to principal axis will be diverging from focus, and that's why this is also known as diverging lens, and convex lens is converging lens. And second rule, if the light ray is passing through focus, sorry, not like this, we'll make on the new page. See, this is F, F to F to F. Now if the light ray is passing through focus, it will go parallel after refraction. That's your second law. And the third law, again I am saying there are 90% chances that question from these law or ray diagram will come in this exam. Concave lens and convex mirror are most important. And the third one, if the light ray is passing through optical center, it will go intact, that means no deviation. So these are basically rules to form image formation in this. And just similar to the convex mirror and concave mirror, we have image formation in convex lens and concave lens. Concave mirror, 6 ray diagrams, 5 real, 1 virtual. Convex, 6 ray diagram. Convex lens, 6 ray diagrams, 5 real, 1 virtual. See, if the light is coming from infinite, after reflection, it will be passing through focus. The image would be real, inverted, and highly diminished. Same, if the object is beyond 2f, the image would be between f and 2f. The image would be real, diminished, and inverted. See this ray diagram. When the object is at 2f, that means same case as of C. The image will also be at 2f, same size, real, and inverted. Now, object is coming from infinite to near the mirror. The image will go from lens. The image will go from lens to away from the lens. So now when the object is between f and 2f, the image would be now enlarged beyond 2f. And when the object is at f, the image would be at the light rays would go parallel and the image would be formed at infinite. This is the case of laser lights and parallel beams. And when the object is kept between f and optical center, the light rays would go diverging, and so we have to extend it in the backward direction to get a virtual image. So in this case, we have to look inside the lens. That means virtual image is obtained in this case. So this is the case of magnifying lens. This is the case of microscope. This is the case of all the cases where lens is used to magnify image. Same, we have two ray diagrams of concave lens. When the object is infinite, the image would be at point size, light diverging from the focus. Second, when the object is nearby the lens, the image is formed backwards, virtual, diminished one. Okay, so these are the two cases where we are getting images in concave lens. Talking about the uses of convex lens and concave lens. So convex lens is used in magnifying lens. This is a convex lens. वो बाबूराव गणपतराव आपटे का चश्मा, आंख बड़ी बड़ी दिखती है. You can see the difference. See, you can see my eye to be bigger than normal, usual. This is because the sixth case is happening, virtual and large. So this is magnifying lens, and the lens I am using right now is concave lens. You can see a smaller image in the lens. See this one here. This is smaller image. See, this is virtual and concave lens. Now, microscopes, telescopes, reading glasses, the defect is known as hypermetropia. In camera lenses, you must have seen the lens, the backward lens of the phones. They have a smaller convex shape. That is convex lens. And these are the 5 uses of convex lens. Talking about the concave lens, eye doors, that door eye which we use, peepholes. The telescopes, the binoculars, we see all the images inside the lens. The binoculars have concave lens. Some projector systems use concave lens to extend their focal length. And eye lens, which I am using right now, myopia. This defect is myopia. I have to keep using spectacles for the whole time. So these are the uses of concave lens. Again, now we are getting on the sign convention of lenses. So all the distances are measured from the center, from the optical center. We are keeping again same Cartesian plane. U is always negative. F of this surface F was here, so F is positive. V, image distance, if the images are real then they are positive, they all are forming here, and if the image is virtual it is forming here. In case of magnifying lens it is negative. If we talk about height of object is always positive, height of image for real is negative, and height of image for virtual is positive. Have I left anything? U, V, F, H naught or HI. Okay, so these are the terms related to convex lens and these are the sign conventions. Talking about the concave lens, see this is a concave lens. This surface have F here. So U is always negative. In this case, F is also negative, and all the images are formed virtual. So V is always negative. Height of object is always positive. Height of image is always positive, because in both the cases we are getting erect image and diminished image. So that is also positive. So these are the terms related to the convex lens and concave lens, and these are the sign conventions. We use same sign conventions as it is to find magnification and to use in lens formula. Now what is magnification? The ratio of height of image to that of height of object gives how much bigger image or smaller image we are getting. So M here is V by U or H of image upon H of object. We have lens formula 1 by F equals to 1 by V minus 1 by U in this case. Plus 1 by U was in mirror case. In lens case, it is minus V by U. Okay. We have one more formula here, that is a power of lens. Now what is power of lens? P is power of lens is reciprocal of focal length. And focal length should be in meters. Meter is the SI unit of distance. It should be in meters. So P is 1 by meter. That means it's diopter. You must have heard the power of lenses. I am using 0.5. That is 0.5 diopter. The D, capital D is the unit, diopter. So 1 diopter is power of lens when the focal length is expressed in meters and is the reciprocal of this focal length. And when the focal length is given in centimeters, we convert it into meter and we get P equals to 100 upon F when F is in centimeter. So make sure to convert it into meters, or if you are using centimeter, it should be 100 upon centimeter. So that was all about the topics covered in light chapter, light, reflection and refraction. We'll be having another lecture in which we'll discuss the numerical section of this chapter. Till then, revise all the concepts, go through all the questions of NCERT, all the in-text questions, all the solved examples, and each and everything, all the PYQs which have come in the previous questions. See you in the next lecture. Now focus on this green light. This green light is the laser light. And now when I lower it on the glass slab cap beneath it, see, there is a deviation inside the glass slab. The incident ray and the emergent ray, these two seems to be parallel. See, this is emergent, these two seems to be parallel, and there is refraction inside. The refracted ray can be seen inside the glass slab, and the distance between these two parallel lines is lateral shift.